So you want to see some hard calculus questions. We'll look at this exam 1 question with a 35% success rate. We'll look at this exam 2 question with a 6% success rate, which is what you would expect if students were guessing, and there were about 17 options. And then we'll have a look at this exam 2 extended response question, which was also pretty tricky. Let's do it. So this was an exam 1 question in 3 parts, but it was really part C that students found most difficult. We'll quickly work through parts A and B. Part A was a show that question, and we've got this formula from the formula sheet, which pretty much gets us most of the way there. If you look at the integral formula on the right, it actually has the x on A inside the inverse cos function, which is exactly what we want. We just then need to apply the product rule. So there it is, product rule, a little bit of simplification to get that expression which we need to show there. So that's part A. Part B was about the domain and range of this function. And again, the formula sheet comes in really useful because they give us the domain and range for inverse cos or arc cos. We just need to adjust it for our function. So for the domain, we've got an x over 2 in there, which is going to mean our domain is going to be -2 to 2 instead of -1 to 1. And for the range, we just need to consider that we're square rooting the inverse cos. So instead of 0 to pi, we're going to have 0 to square root pi. All right, so then we can move on to part C, which is the volume of a solid of revolution. But what we've done in parts A and B is still going to be obviously useful. Our function is the square root of an inverse cos. So when we calculate our integral, we expect that this derivative formula is going to be useful. But let's visualize a graph first, okay? So we know what an inverse cos graph looks like. So with the square root, we're just going to bring everything down a little bit. The shape is going to be roughly the same. Then we're going to rotate that around the x-axis. So if we can visualize a solid of revolution there, it looks a bit like a bell type shape. But then we're going to find that volume using our formula for the solid of revolution around the x-axis. So that's why we've got a f of x squared dx there. So because we have a square root function and we're squaring it, it's actually going to simplify the function quite a bit. One thing to keep in mind is that pi, if you're anything like me, sometimes it goes missing. So try not to forget in our solid of revolution, we have a pi out the front there. All right, so simplifying the getting rid of the square root there, this is our integral which we need to evaluate, and we're going to use this formula. So just rewriting it as an integral. And what we're interested in is the integral of the inverse cos. So it's in there, but we just need to separate out that second term. So we're going to split up that integral. Okay, pull that over to the other side. So our volume is going to be the left-hand side, which has already been integrated. Okay, you just need to sub in the terminals to a -2. And then pull over that integral from the right-hand side by adding it to both sides. And that one we obviously still need to anti-differentiate, but that's something we can do. All right, also, don't forget the pi. That was intentional, but just whack a big old pi out the front of everything there. All right, so we're getting there. We just need to evaluate this integral on the right. We'll probably do that using a u substitution with 4 minus x squared. The du dx would be -2x. So subbing that in, we have an x on the top, so that's going to be -1/2 of -2x. But actually, if we look at the terminals, so we're subbing in x equals -2 and +2, those terminals on top and bottom are both going to give us 0. So which means that we're integrating from 0 to 0, we don't care what's inside, the whole thing is just going to have a value of 0. So that's actually really good because we only then need to worry about that first term, which has already been integrated. We just need to sub in +2 and -2, and then inverse cos of 1 minus inverse cos of -1, we get our answer. So that was an example of a hard exam 1 question. I think the key takeaways are, don't forget the pi, sketch a graph so you can see the function, and just be careful with your positives and negatives. Okay, so with this multi-choice question, I mean, even just looking at it, we can tell that it's a hard question. For the information we've been given, it's an unknown function. We know the first and second derivatives are defined, and we're given some information about some points on the original function, and we're actually given a second derivative function, which is, I mean, it's something. It's also got another function g inside the second derivative function there. So, and we asked about the coordinates of any points of inflection of the modulus of f. Right. Okay, so for points of inflection, what do we know? Well, they occur when the second derivative not just is 0, but actually changes sign. Okay, so not only does the second derivative have to be 0, it has to be like negative to the left and positive to the right, or vice versa. It actually has to change, which means there's a concavity change. It's an important point, and I've actually got another video which explains points of inflection in a bit more detail, so definitely check that one out if you're interested. But for this question, so we want to find, firstly, when is that second derivative going to be 0? That's going to occur when x is negative a or positive b. But again, that's not enough, right? We still need to check whether the concavity is actually going to change, whether the sign of this function is going to change. So, well, we can have a look at the graph of, I mean, this function here is on the top of the second derivative, and that one, we can understand the graph of that, right? So it's going to be a cubic. It's going to have a turning point at negative a and an intercept at b. So, I mean, if we say that a is negative, for example, it's going to look something like that. And whether a is negative or positive, it doesn't really matter. It's going to have a turning point at x is equal to negative a. So it cannot have a point of inflection there because the second derivative is not changing sign, right? If it's negative, it's going to stay negative. If it's positive, it would stay positive. So the concavity can only change at x is equal to b. So that is the only point where we can have a point of inflection. Now that rules out basically most of the options and leaving only b or e. To figure out that, well, we're given the the y coordinate of b is a -1, but then because this is a modulus function, we just make it +1, right? So the point of inflection is going to occur at b, 1. The most incorrect responses were these ones with -a as well. So it's not realizing that the point of inflection is only going to occur when the concavity changes. Alright, so this is exam 2 from the year 2020. It's asking about the function x squared e to the -x. But the tricky part was when we then, later on in the question, generalized to x to the n e to the -x. And in part part 2, students were asked to investigate how many points of inflection would occur for different values of n. So it's going to rely on parts D and E where we were asked for the second derivative. That we can do on the CAS calculator. Okay, so either TI Inspire or Casio ClassPad would have no trouble calculating a second derivative and solving when that second derivative is 0. Even for a general value of n. So that's quite good. We can do that on the CAS calculator. Note that we've only been asked about the non-zero solutions. Because if x was 0, then yeah, second derivative will be 0. But we only asked for the non-zero values, so there'll be 2 solutions there in terms of n. Alright, so for a point of inflection, as we said before, the second derivative not only has to be 0, it also has to change sign. So just knowing when the second derivative is 0 is actually not enough. We really need to investigate a graph, but because this is exam 2, we can now get out our CAS calculator and start having a look at some graphs. So if we type that function in a graphs page, x to the n e to the -x, actually we have the option to create a slider for n, which is exactly what we want, right? We want to try different integer values of n and see what the graph looks like. The first, probably easiest value to try is n is equal to 0. Well, in that case, the function is just e to the -x. It doesn't have any points of inflection. And then we could notice what happens when n is negative. Well, actually, we're going to get an asymptote on the y-axis there. So that cannot be a point of inflection. Neither of the other ones can exist because the other ones had a root n in it. So whenever n is 0 or less, we're going to get no points of inflection. When n equals 1, we actually get 1 point of inflection. So you can probably tell there in the graph. But the reason is because n minus root n is actually equal to 0. So it's not a point of inflection there, but n plus root n is a point of inflection. So 1 point of inflection when n is equal to 1. Then if we try n equals 2, what we can see is there's actually a turning point at the origin, but we do get another point of inflection. That's the n minus root n1. So we're actually having 2 point of inflections there because the origin is not a point of inflection. This is not a proof, this is just demonstrating using the CAS calculator, but when n equals 4, we see the same thing happens. So we get the same pattern whenever n is even. When n is even, then we're going to get 2 points of inflection. So we can write that as 2k whenever k is a positive integer. For odd n, so if we try 3, we see we do get another point of inflection at the origin. And that again happens when n is equal to 5. Probably just need to zoom out to show that. But we get 2 points of inflection at n plus or minus root n. We still get the one at the origin. So that's going to be 3 points of inflection whenever n is an odd integer greater than 1. To actually prove that those are points of inflection, we would need to prove that there's a concavity change at those number of x values for those different n values. But in the exam situation, it's just not time for that. I mean, the intention of this is a CAS question, investigate the graph shape with the CAS, and notice the patterns. All right, we'll leave it there. See you next time.